Welcome to the deep dive. If you've been fascinated by the explosion of generative AI, you've probably seen the incredible applications it's unlocked.
Hmm.
Writing code, composing music.
Right.
But have you ever wondered what it truly takes to build and operate these powerful systems in the real world? It's far more complex than just asking ChatGPT a question.
That's exactly right. I mean, what truly surprised many of us when tools like ChatGPT first appeared wasn't just their raw capability, though that was impressive.
Yeah.
It was the sheer number of applications that just exploded overnight. We'd known since, breakthrough papers like AlexNet back in 2012, that scaling up a model generally improves it. That wasn't new.
Okay.
But the rapid, diverse applications, that felt like a profound, almost dizzying expansion of possibilities. Really surprising.
So today, we're taking a deep dive into this whole area of AI engineering. We'll be drawing insights from a leading book in the field to give you, hopefully, a shortcut to understanding the essential aspects. Building, evaluating, operating these systems. Think of it as like a crucial bridge between traditional machine learning and this new world of foundation models. Our mission: to help you understand what's most important in this rapidly evolving landscape. Expect plenty of surprising facts and maybe some aha moments.
And we'll unpack why real-world AI apps often combine both traditional machine learning approaches and these powerful foundation models. It's not always one or the other. And we'll see how this new engineering discipline has, well, really emerged as one of the fastest-growing fields in tech.
Okay, let's start right there. You mentioned that moment of disorientation when ChatGPT first hit the scene and that explosion of applications. What were some of those initial, almost unbelievable uses that really caught the attention of AI engineers? What made people sit up and say, wow?
It was a sudden, just undeniable jump in possibilities across almost every sector. It wasn't gradual. We saw applications emerge really rapidly,
Yeah.
spanning everything from consumer products to, complex enterprise solutions.
Like what specifically?
Well, think about how AI is now profoundly impacting things like coding. It's not just generating little snippets anymore. It's completing entire functions, suggesting improvements, even debugging pretty complex code bases. That's a huge leap.
Definitely.
Then there's image and video production. This ranges from simple photo and video editing tools, which are getting pretty sophisticated, all the way to generating entire design concepts for marketing campaigns, or even creating original digital art from scratch.
And writing, I imagine.
Oh, absolutely.
All right.
Writing. Beyond just drafting emails or social media posts, which it does okay, AI is handling complex copywriting, optimizing content for SEO, generating comprehensive structured reports from just raw data. It's quite powerful. Education is another big one. And this goes far beyond just summarization, which was kind of the first wave.
Okay.
Now, AI can generate personalized lecture plans, adapt materials to different learning styles, like maybe you're an auditory learner, can read things aloud, or if you prefer visual examples, it can adapt them with themes you enjoy, like animals or something.
Huh, interesting.
Yeah. It can create quizzes tailored to specific knowledge gaps and even act as a tireless debate partner. I mean, we even saw a direct market impact, remember. Companies like Chegg saw their share price plummet because students started turning to AI for homework help.
Wow, yeah, I remember that.
Then conversational bots. We're seeing everything from standard customer support and general chat bots to these really specialized product copilots.
Product co-pilots.
Yeah, they guide users step by step through complex processes, like filing an insurance claim or setting up some complicated software, really holding you hand through it.
Okay. And information sorting.
Yep. Information aggregation.
Yeah.
Things like summarizing dense documents instantly, enabling those talk to your docs features where you can just ask questions about a PDF,
Right, I've seen those.
and performing pretty in-depth market research analysis. Then there's data organization. Think about automated image search, like how Google Photos can find pictures of your dog at the beach.
Yeah, that's amazing.
Or extracting highly structured information, say credit card details or specific contract clauses, from just massive amounts of unstructured text. That's a huge time saver.
Definitely.
And finally, workflow automation. This is about handling those repetitive rule-based tasks. Things like travel planning, lead management and sales, and interestingly, even synthesizing data to train more powerful models in the future, using AI to build better AI.
Okay, so these foundation models are incredibly versatile. They can do a mind-boggling range of tasks right out of the box. But if they're so powerful, does that actually make the engineering job, I don't know, easier? Or does it bring a whole new set of challenges because they're so versatile, maybe unpredictable?
That's a great question, and it gets right to the heart of AI engineering. Building with these foundation models means you really have to understand what they are and how they're put together. Even a high-level grasp of their inner workings helps you decide, okay, which models should I use? How do I adapt them for my specific needs? And crucially, what are their limitations? You can't just treat them like magic boxes.
Okay, let's unpack that then. What's the core knowledge? What truly defines these models from an engineering perspective? What do you need to know?
Well, first and foremost, training data is king. Seriously. An AI model is quite literally only as good as the data it was trained on. There's no magic beyond the data.
Right.
And we see this so starkly in performance differences for languages other than English. You look at benchmarks like MMLU, that's the Massive Multitask Language Understanding Benchmark.
Okay.
It tests a model's knowledge across a huge range of subjects. Well, GPT-4 performs significantly worse in underrepresented languages like Telugu compared to English. And when solving math problems, it's something like 3 times better in English than in Armenian or Farsi. This really highlights the critical need for domain-specific models if you're working with unique data, like maybe protein structures for drug discovery. You can't just rely on a general English model.
Makes sense. What else?
Second, you have to consider model scale and cost. The sheer scale of these things is just staggering. GPT-3 175B, for example, that needed over $4 million just for compute during its initial training. And that's just compute cost.
Wow.
And we define model scale not just by its number of parameters, that's the number of people often quote.
With the billions of parameters.
Exactly. But it's also crucially about the number of tokens it trained on and its FLOP's floating point operations. Think of FLOPs as the raw computational horsepower needed. These models require literally exaflops of computation that consumes energy on a scale that, well, it can rival small cities.
That's incredible.
It's not just a technical detail. It's a critical infrastructure and environmental concern that engineers absolutely have to grapple with.
That's an incredible cost and energy footprint. So given that investment, you'd assume bigger always means better, right? More data, more parameters, better model. But I think I've heard about something called inverse scaling. Can you explain that? It sounds like it kind of defies that logic, maybe even introduces new problems.
You've hit on something really fascinating and, yeah, a bit unsettling, actually. It challenges our basic assumptions. Inverse scaling, it refers to this counterintuitive phenomenon where, in some specific cases, putting in more alignment training can actually lead to models that align less with human preferences.
Less. How does
Yeah.
that work?
Well, sometimes they start expressing specific political or religious views more strongly, for instance, even when you're trying to make them more generally helpful and harmless. Imagine spending millions to make your AI super polite and helpful, only to find it somehow becoming less aligned with what you actually intended.
That sounds problematic.
It really is. It's not just some quirky research finding. It fundamentally challenges the idea that more training always equals better or safer AI. It reveals this really complex, almost paradoxical relationship between scale, training, and control. And that's a massive ongoing challenge for AI engineers.
So scaling up isn't a simple path forward then.
Not at all. And this leads us to some critical bottlenecks for future scaling. First, there's a realistic concern that we might actually run out of high-quality, human-generated internet data in the next few years. There's only so much text and images out there.
Run out of data? Really?
High-quality data, yeah. So if new models are then recursively trained on AI-generated data made by other AIs, some researchers worry this could lead to model collapse.
Model collapse.
Yeah, where the models gradually forget the original data patterns, maybe become less diverse, less creative, kind of converging on some average, maybe bland output over time.
Okay, that's one bottleneck. What else?
Second, electricity. It sounds mundane, but it's huge.
Yeah.
Data centers are already consuming maybe 1–2% of global electricity.
Wow.
And estimates suggest that could reach anywhere from 4% to maybe even 20% by 2030. That could lead to significant power shortages and major infrastructure strain. It's a real physical limit.
So even after that massive pre-training on all that data dealing with those costs and limitations, there's still a significant amount of work needed to make these models behave in a way that's actually useful and, safe for humans.
Yes, absolutely. That initial pre-training is just the start. That's where post-training comes in. This is all about aligning the models with human preferences, making them helpful, honest, and harmless.
How's that done?
Techniques like supervised fine-tuning, SFT, and especially reinforcement learning from human feedback, RLHF, are key here.
RLHF, right. Heard a lot about that.
Exactly. But this alignment process is very expensive. For example, it apparently cost OpenAI something like $130,000 just to label 13,000 prompt response pairs for InstructGPT, which was a precursor to ChatGPT.
$130,000 for 13,000 examples. That's a lot of human effort.
It is, and it involves training a separate reward model, basically.
Oh.
Another AI that learns what humans prefer. And interestingly, they often train this by asking human labelers to compare two different responses and pick the better one, rather than giving an absolute score.
Why compare?
It turns out comparison is often easier and more reliable for humans than trying to assign a score out of 10, for example. It makes the labeling process more efficient and consistent.
Okay, that makes sense. Now, one of the things that continually fascinates me, and sometimes, frankly, frustrates me about these models are their, let's call them personality quirks, like when they just make stuff up, hallucinate, or give different answers to the same question. How do AI engineers actually approach these probabilistic behaviors? Is it about trying to eliminate them entirely, or more about learning to work with them?
That's a perfect way to put it, personality quirks. And yeah, it's fundamentally due to sampling, the probabilistic way the model constructs its outputs, token by token.
Probabilistic, meaning not deterministic.
Exactly. It's not like a calculator giving the same answer every time. And this probabilistic nature is precisely what makes AI great for creative tasks, right? It can brainstorm limitless ideas.
Sure.
But it's also the root cause of inconsistency, giving different outputs for the same input and hallucinations, where the model confidently just makes up facts that aren't true.
Why does it hallucinate, though? Is there a theory?
Well, one intriguing hypothesis is that the model struggles to differentiate between the data it was trained on and the data it generates itself. So it might start expanding on its own previous statements, leading it down a path of sort of self-delusion, if you will.
Self-delusion. Okay. So given all this complexity, these quirks, this probabilistic nature.
Right. Given all that, the biggest hurdle in actually bringing AI applications into production, into reality, is often evaluation itself.
Yeah.
How do you know if it's working well enough?
Right.
Many people, maybe starting out, they settle for word of mouth or just kind of eyeballing the results. Yeah, that looks okay.
Which sounds risky.
It's incredibly risky when you're building robust systems that people rely on. We absolutely need systematic, rigorous evaluation.
That makes perfect sense. So what are the different ways we assess if an AI is actually good or useful for our specific needs, beyond just a gut feeling or eyeballing it?
Yeah, there are several metrics and methods we look at. First, for just basic language modeling metrics, one common approach is perplexity.
Perplexity.
Yeah, it essentially measures how accurately or how surprised a model is by a sequence of text. Lower perplexity generally means it's better at predicting the next word.
Okay.
But here's a counterintuitive thing. Sometimes a model's perplexity can actually increase after that post-training alignment we talked about.
Increase. Isn't that bad?
Not necessarily. It's because the model's being taught to complete specific tasks, like answering questions helpfully, not just predict the most likely next token in any sequence. So it might become less predictable in a general sense, but better at the actual job you want it to do. It's a subtle but important trade-off.
That's a great point about the trade-off. So perplexity measures basic prediction, but how do you rigorously evaluate those more open-ended, free-form responses? The stuff generative AI is really known for.
Right. For evaluating open-ended responses, we need a richer toolkit. We dive into several criteria. First, we look at functional correctness. This covers a few things, like factual consistency, making sure the outputs actually align with any given context or known facts.
How do you check that automatically?
Well, one way is to break the output down into individual factual claims, like the SAFE approach does, and then check each claim against an external source, maybe like a search engine or a database. Functional correctness also includes safety detecting harmful outputs like toxicity, bias, or leaking personally identifiable information, PII. And it includes strict instruction following. Did the model actually adhere to the format or content rules you gave it in the prompt?
Right. Did it give me JSON when I asked for JSON?
Exactly. Then there are similarity scores. We could use lexical similarity, which is pretty basic, just based on overlapping words. Or, much more powerfully, semantic similarity, which uses embeddings to understand the underlying meaning, even if the words are different. It's just the same.
Embeddings. Okay. That sounds more useful for complex answers.
It usually is. Then there's a fascinating, almost meta approach using AI as a judge.
Using AI to judge AI.
Yep. You essentially prompt another AI model, maybe even a very powerful one like GPT-4, to evaluate the first AI's output based on specific criteria you give it.
Like what?
Like asking, does this response sound like Gandalf? Or Rate this product description's trustworthiness on a scale of 1 to 5. It can be surprisingly effective and efficient.
But what are the catches?
Well, it has limitations, of course. The Judge AI is also probabilistic, so its judgments aren't perfectly consistent. It can add latency and cost. And fundamentally, the Judge itself is an AI with its own potential biases and blind spots. Yeah, it's not foolproof.
Right. What else is in the evaluation toolkit?
Finally, comparative evaluation is really popular. You see this prominently in public leaderboards like the LMSYS chatbot arena, or even directly within products like ChatGPT, where you can thumbs up or thumbs down responses or choose which one is better.
Ah, the A/B test for responses.
Essentially, yes. Users are presented with two side-by-side outputs and asked to pick a winner. It's excellent for gauging human preference. What do people like more?
But preference isn't always correctness.
Exactly.
Yeah.
That's the downside. It doesn't always reflect factual correctness. And these comparisons can sometimes be skewed or polluted by users submitting very simple or leading prompts that don't really test the model rigorously.
Okay, so it's clearly not just about finding the single best model in some abstract leaderboard sense, but finding the best for your application. How do AI engineers actually make that crucial choice? And then how do they design a reliable, systematic evaluation process tailored to their needs?
That's the key question. When it comes to model selection, you start by considering what we call hard attributes. Things like the model's license, can you actually use it commercially? Its size, will it fit your infrastructure? And the sources of its training data, are there potential biases or contamination issues you need to be aware of?
Okay, the non-negotiables first.
Right. Then you move to soft attributes. Things like accuracy on specific tasks, toxicity levels, latency. These are often things you can potentially improve through further engineering, like fine-tuning or better prompting.
An open source versus API.
That's a big decision. You have to carefully weigh using open source models, which give you more control but require more infrastructure, against proprietary APIs, which are easier to use but mean less control, ongoing costs, and relying on their safety guardrails. Public leaderboards can give you a broad overview, but again, you must watch out for data contamination, where models might have basically memorized the benchmark answers during training.
So you need your own tests.
Absolutely. Which brings us to designing your evaluation pipeline.
Yeah.
This is absolutely crucial for success. You can't just wing it.
What does a good pipeline involve?
First, you have to evaluate all components of your system. If your application fails, maybe it gives a wrong answer. You need to know exactly where in your pipeline the failure occurred. Was it the retrieval step, the model itself, the output parser?
Yeah.
You need that visibility.
Not just it broke.
Exactly. Second, you must create a detailed evaluation guideline. This means explicitly defining what good means for your specific application in detail. The LinkedIn example is great here.
Remind me.
They found that a technically correct response for a job assessment, like telling someone you are a terrible fit, was absolutely not a good response from a user experience perspective. It wasn't helpful or constructive. So good is context dependent.
Right. Defining success beyond just technical accuracy.
Precisely. Third, and this is vital for getting resources, you need to tie your evaluation metrics to business metrics. Translate something technical like 80% factual consistency into concrete business impact, like re-anticipate we can automate 30% of Tier 1 customer support requests. This helps justify the investment and shows the actual value.
Speaks the language of the business.
Exactly. And finally, you need to meticulously define your evaluation data. Don't just use a random sample. Use data slicing to make sure you're evaluating performance across different important user groups or query types.
Why is slicing so important?
It's crucial for avoiding pitfalls, like Simpson's paradox. That's where a model might look like it's performing well overall, on average.
Okay.
But when you actually slice the data and look at specific, crucial segments, maybe queries from new users or queries about a specific product, it's actually performing worse on every single segment. The average hides the real story.
Wow, that's tricky.
It is. You also need techniques like bootstrapping, basically, resampling your test data to make sure your evaluation results are statistically reliable and not just a fluke of the specific test set you used. OpenAI even offers rough guidelines on how many samples you might need to be, say, 95% confident that one model is truly better than another based on the score difference.
Okay, that's a lot to think about just for evaluation. So we've covered understanding the models, their quirks, and how to rigorously assess them. Now let's pivot from understanding to actively guiding them. You've picked your model, you know how to evaluate it. But how do you actually get this complex, probabilistic system to do exactly what you want it to do? This brings us to prompt engineering. It's often simplified down to just fiddling with words. But it sounds like it's far more sophisticated than that.
It really is. It's much more like developing effective human-to-AI communication protocols. And yeah, it involves some truly ingenious solutions sometimes. But it also highlights the often surprising sensitivity of these models.
Just sensitivity.
Yeah, sometimes even tiny changes in the prompt, like writing the digit 5 instead of the word 5, can drastically alter the model's response, especially if the model isn't particularly robust or well-trained on handling variations. It's not always intuitive.
So, what are the best practices for communicating effectively with an AI? How do you write a good prompt?
Well, first, write clear and explicit instructions. Sounds obvious, but it's key. You need to be absolutely unambiguous about what you want. Specify the exact output format you need, give me JSON, or respond in bullet points, or explicitly state, do not include any introductory preamble.
Be direct.
Very direct. And use clear markers to signal the boundaries of your instructions, maybe using triple quotes, XML tags, or markdown formatting. Help the model understand what's an instruction versus what's context.
Okay, what else?
Second, give the model time to think. This is fascinating. Techniques like chain of thought, prompt, and cuff have shown really surprising improvements.
Chain of thought.
Yeah, where you explicitly ask the model in the prompt to think step by step or reason through the problem before providing the final answer. It's like asking someone to show their work in math class.
And that actually helps.
It often significantly improves reasoning abilities and reduces hallucinations, especially on complex problems. It forces a more structured thought process.
Interesting. Any other prompting techniques?
And third, consider prompt decomposition. If you have a really complex task, break it down into simpler, manageable subtasks. Maybe have the model do step 1, then use that output for step 2, and so on.
Why break it down?
It not only tends to boost the overall performance because each step is easier, but it also makes monitoring and debugging infinitely easier. If something goes wrong, you know which subtask failed.
Okay, clear instructions, give it time to think, break down tasks. What about the flip side? What about when malicious actors try to trick the AI into doing something harmful or revealing sensitive information?
Ah, yes, that's a critical and challenging area known as defensive prompt engineering. We're talking about protecting against various attacks.
Like what kind of attacks?
Things like jailbreaking, where users try clever prompts to bypass the model's built-in safety guardrails and get it to generate harmful content.
Right, I've seen examples of that.
Or prompt injection, which is particularly insidious. This is where malicious instructions are hidden within data that the AI retrieves and processes.
Hidden in the data.
Well, imagine an attacker put some malicious instructions or even code into a public web page or a GitHub repository. If your AI application uses web search or accesses that repository to answer a user's query, it might inadvertently retrieve that malicious instruction and execute it or be influenced by it.
Wow, that's sneaky.
It is. We also see information extraction attacks, where prompts are designed to trick the model into revealing confidential data it might have access to, violating privacy, or even getting it to regurgitate large chunks of copyrighted material it was trained on. Defending against these is a constant cat-and-mouse game.
Okay, so prompting is key, but sometimes the model just doesn't know the answer, right? What if the information needed isn't in its training data, maybe because it's too new, like current events, or it's specific internal company knowledge?
That's a very common and important scenario. And that's where retrieval augmented generation, or RAG, becomes absolutely indispensable.
RAG. Okay, how does that work?
So unlike a standard model that just relies on its massive but static pre-trained memory, a RAG system acts more like an AI with an open textbook or access to a live research assistant.
Okay.
Before generating an answer, it first retrieves relevant, up-to-date information from external knowledge bases like company documents, a vector database, or even the live web. It then feeds this retrieved context into the prompt along with the user's original query.
Ah, so it gives the model the relevant facts right before it answers?
Exactly. This dramatically improves factual accuracy, especially for information that changes quickly or is very specific. It also helps reduce hallucinations because the model has the ground truth right there. And it's often far more cost-effective than constantly retraining or fine-tuning massive models with new information.
How does it find the right information to retrieve?
That's the retrieval part. It often uses embedding-based retrieval. Instead of just matching keywords, it looks for documents or text chunks whose meaning, represented by embeddings, is semantically similar to the user's query. This ensures it fetches truly relevant context, not just stuff with overlapping words.
So RAG gives the model timely facts, This sounds like we're starting to give the AI tools or capabilities to interact with the outside world beyond just text generation. Is that where the idea of agents comes in?
Precisely. AI agents represent the next level of complexity and autonomy. You're moving beyond just generating a response to a single prompt.
So what does an agent do?
Here, the AI foundation model acts as a kind of sophisticated brain or controller.
Yeah.
And it doesn't just process information, it plans sequences of actions needed to accomplish a larger goal. Yes, it might break down a complex request like, plan a trip to Paris for me next week, into steps, check flights, find hotels, look for activities, etc. Then, crucially, it can use external tools to execute those steps, like calling an airline API, executing a SQL query on a database, performing web searches, or interacting with other software.
So it can actually do things.
It can take actions. And then there's often a reflection step, where the agent evaluates the outcome of its actions, checks if the goal is accomplished, maybe self-corrects if it made a mistake, and learns from the process.
So it's like a mini project manager running on AI.
That's a good analogy. It raises some really fascinating and difficult questions about how well these foundation models can actually plan and reason over multiple steps beyond just simple execution. It's a very active area of research and development.
Okay, so we have prompting, RAG, agents. But what if even those aren't quite enough? What if you need the model to adopt a very specific style, or understand nuances in your company's jargon, or perform a task that's just too different from its general training?
Right. In those cases, even sophisticated prompting or RAG might hit a ceiling. That's when you might turn to fine-tuning.
Fine-tuning, so actually retraining the model.
Sort of. It's about continuing the training process of an already pre-trained model, but using your own smaller, curated data set of specific examples relevant to your unique domain or task.
Okay.
It's definitely a more resource-intensive step than just prompt engineering. You need data, compute, expertise, but it allows for deeper customization of the model's behavior, style, and knowledge.
When would you choose fine-tuning over RAG or vice versa? Is there a rule of thumb?
There's a useful, though maybe slightly oversimplified, rule of thumb people often use. Fine-tuning is for form, and RAG is for facts.
Form versus facts. Explain that.
RAG is generally better when the main goal is to provide the model with up-to-date or specific external knowledge to improve the factual accuracy of its answers. Fine-tuning, on the other hand, is often better when you need the model to learn a specific style, format, tone, or understand and follow very specific syntaxes or nuanced instructions consistently. You're teaching it how to respond, more than what facts to use.
Okay, that's a helpful distinction. But fine-tuning these huge models sounds computationally expensive, maybe even impossible for smaller teams.
It definitely can be. Fine-tuning large models traditionally has significant memory bottlenecks. You need massive amounts of GPU memory to hold not just the model's parameters, but also things called activations, gradients, and optimizer states during training. It adds up fast.
So how do people manage that?
Well, several techniques help. One is quantization. This involves reducing the precision, the number of bits used to represent the numerical values, the weights and activations, in the model. Sometimes you can go down to 8 bits, 4 bits, or there's even research on 1-bit LLMs. This drastically reduces the memory footprint.
Lower precision doesn't hurt performance too much.
There's often a trade-off, but clever techniques minimize the impact. But perhaps the biggest game changer for making fine-tuning more accessible is parameter-efficient fine-tuning, or PEF.
P.
Yes, and particularly a very popular technique within PEF called LoRA, which stands for low-rank adaptation.
LoRA. Okay, what does that do?
Instead of retraining all the billions of parameters in the original model, LoRA freezes the original model and trains only a very small number of new additional parameters organized into low-rank matrices. It might only train, say, 0.1% or 1% of the total parameters.
And that works just as well.
Surprisingly often, yes, for many tasks. It drastically reduces the memory and compute requirements for fine-tuning, making it far more accessible. And these small LoRA adapters are modular. You can train different adapters for different tasks and just plug them into the base model as needed. You can even share and reuse them.
Wow, okay. LoRA sounds pretty significant for democratizing fine-tuning. But even with PEFT, the data you use for fine-tuning still matters immensely, right?
Oh, absolutely. It always comes back to the data. So this brings us to dataset engineering. What goes into creating that ideal dataset, whether for fine-tuning or even for pre-training?
It sounds critical.
It is. The old mantra holds true. The quality of a model depends directly on the quality of its training data. And in this new AI era, High-quality proprietary data is increasingly becoming a key competitive advantage. Dataset engineering is this whole specialized field focused on meticulously creating, cleaning, and curating that ideal high-quality dataset.
Is the focus shifting more towards data now?
Definitely. We're seeing a significant shift in the field towards data-centric AI. The idea is that often the biggest improvements come not from endlessly tweaking the model architecture, but from rigorously improving the data itself.
Any evidence for that?
Yeah, studies have convincingly shown that a relatively small amount of high-quality data can outperform a large amount of noisy data. For example, one well-known study found that just 1,000 carefully curated, high-quality prompt response pairs could make a 65 billion parameter model perform comparably to the much larger GPT-4 on certain tasks. Quality over quantity.
Quality. What defines quality in this context?
It means the data must be aligned with the desired behavior, it needs to be consistent internally, and it needs to be diverse enough to cover the range of scenarios the model will face.
But what if you just don't have enough high-quality human-generated data? It seems expensive and time-consuming to create.
That's a very real challenge. And that's where techniques like data augmentation and synthesis become vital tools.
Using AI to make data for AI.
Exactly. AI itself can be used to generate new training data. This could involve transforming existing data, like paraphrasing sentences, or translating or creating entirely new examples from scratch, perhaps based on some initial seed examples or instructions.
Is this common?
Very much so. We saw models like Alpaca, for instance, which were famously trained primarily on around 52,000 instruction response pairs that were actually generated by another powerful AI like GPT 3.5.
Using AI to bootstrap AI training, but doesn't that bring back the model collapse concern you mentioned earlier?
It absolutely does. That's the crucial risk. Recursively training new AI models primarily or exclusively on AI-generated data can degrade performance over time. The models might start overrepresenting common patterns they see in the synthetic data and gradually forget or underrepresent rare, unique, or nuanced information from the original human distribution. It's a major area of ongoing research how to use synthetic data safely and effectively without falling into this trap.
So even with all these sophisticated tools and algorithms for data generation, data curation, fine-tuning, is there still a place for just good old-fashioned, rigorous human review of the data, sitting down and looking at it?
Absolutely. Unequivocally, yes. There's a great quote, something like, manual inspection of data is probably the highest value to prestige ratio of any activity in machine learning.
High value, low prestige.
Exactly. It might not seem glamorous, but carefully looking at your data samples helps you find those subtle errors, inconsistencies, unexpected biases, or edge cases that automated tools and metrics might completely miss. It's crucial for truly understanding what your model is learning and ensuring your data actually reflects your intentions. Never underestimate the power of just looking at your data.
Okay, solid advice. So let's say we've engineered our data, maybe fine-tuned our model, evaluated it rigorously. It's ready. Now, the next significant challenge is getting it to run efficiently when users actually interact with it, right? Making it fast and affordable in the real world.
Precisely. That whole area is called inference optimization. This is where your AI application transitions from the development environment to practical, everyday use, handling potentially thousands or millions of user requests. And performance here is critical.
What are the key performance metrics we're primarily trying to improve during this inference stage? What matters most to the user and the bottom line?
We mainly focus on two key things, latency and throughput.
Latency and throughput. Break those down.
Okay, latency has a couple of aspects for generative models. There's time to first token, TTFT. How quickly does the user start seeing the beginning of the response? That affects perceived responsiveness.
Right, you don't want to stare at a blank screen.
Exactly. And then there's the subsequent token generation speed, often measured in tokens per second. How fast does the rest of the response stream out? Throughput, on the other hand, is about system capacity. How many requests can the system handle simultaneously per second?
And both impact user experience and cost.
Directly. Lower latency means happier users. Higher throughput means you can serve more users with the same hardware, which lowers costs. There are lots of techniques to optimize these. One interesting one is speculative decoding.
Speculative decoding sounds intriguing.
Yeah, the basic idea is you use a much smaller, faster draft model to quickly generate a sequence of likely next tokens. Then, the main, larger, more powerful model verifies this draft sequence in parallel, much faster than generating token by token itself. If the draft is correct, you accept the whole chunk. If not, you correct it and continue. It can significantly speed up generation.
Clever. Using a small model to help the big model go faster. So it's clear it's not just about the core AI model itself, but the entire AI engineering architecture that surrounds it to actually deliver the service to the user effectively. What does that surrounding architecture typically look like, even for a relatively simple AI app?
You're absolutely right. Even the simplest AI application can get surprisingly complex pretty quickly once you move to production. It starts, of course, with that basic user query model response flow.
Okay, the core loop.
But then you immediately start adding crucial layers around it to make it robust, safe, and efficient.
Like what kind of layers?
Well, one key layer is enhancing context. This often involves integrating R, like we discussed, giving the model access to external data sources or tools so it's not limited to just its static training data.
Providing the necessary background info.
Exactly. Then you have guardrails. These are absolutely crucial for safety and quality control, especially when dealing with user input and model outputs.
Input and output guardrails.
Yes, input guardrails might automatically detect and mask sensitive data, like credit card numbers or PII, before it even gets sent to the model, especially if you're using a third-party API, to prevent leaks.
Sure.
And output guardrails operate on the model's response. They try to catch things like hallucinations, toxic or biased language, or maybe gently refuse to answer questions that are clearly out of scope for the application. They're like safety nets.
Okay. Context enhancement, guardrails. What else?
We also often implement caching to improve speed and reduce cost. This could be simple exact caching if the exact same query comes in again. Just reuse the previous response.
Makes sense.
Or you can use the more advanced semantic caching. This tries to identify if a new query is semantically similar enough to a previous one, even if the wording is different, and reuse the old response.
That sounds powerful, but maybe risky.
It is potentially risky. Semantic caching can be tricky to get right. If your similarity threshold is wrong, you might incorrectly reuse an answer, leading to subtly wrong or inappropriate responses. It needs careful tuning and evaluation.
Got it. Any other major architectural components?
And finally, for more complex applications involving multi-step tasks, we start implementing those agent patterns we talked about earlier. This involves building those agentic loops that allow the AI to plan, execute tools, gather information over several turns, and reflect on its progress towards achieving a larger goal. The architecture gets much more sophisticated then.
Okay, so you've built this whole system model, context, guardrails, maybe an agent loop, it's deployed. How do you know if it's actually working as expected out there in the wild? And maybe more importantly, how do you quickly diagnose problems when they inevitably occur?
Yeah, that's where robust monitoring and observability become absolutely essential. It's not enough to just launch it and hope for the best.
What do you monitor?
We track crucial metrics over time. Things like the rate of factual consistency, the measured toxicity or bias levels in responses, the overall cost per query, the query volume, latency error rates, all the key performance and quality indicators.
Just watching the numbers?
Well, the numbers give you the high-level view, but often they don't tell you why something went wrong. That's where detailed logs and traces come in. Observability tools allow you to trace a single problematic query step by step through the entire complex architecture. You can see the retrieved documents, the exact prompt sent to the model, the raw output, how the guardrails processed it. This lets you pinpoint exactly where a failure occurred, which is crucial for debugging.
So you can replay the whole interaction?
Essentially, yes.
Yeah.
That level of visibility is key.
Ultimately, though, the system is interacting with real people. How do our users, the people using the AI every day, help make the AI even better once it's deployed? How do we close that loop?
User feedback is truly invaluable. It's arguably one of the most important components of a successful, evolving AI application. It's not just about evaluating performance anymore. It's a continuous proprietary data source.
A proprietary data source.
Yeah, the feedback your specific users give on your specific application is unique to you. It creates a powerful data flywheel. You use the feedback to improve the model of the system, which leads to a better user experience, which encourages more usage and more feedback, and so on. It can become a significant competitive advantage over time.
What kinds of feedback are useful?
We generally distinguish between explicit feedback and implicit feedback.
Okay.
Explicit feedback is when the user directly tells you something like clicking a thumbs up or thumbs down button, giving a star rating, or maybe correcting a wrong answer.
Straightforward. What's implicit?
Implicit feedback is inferred from observing user behavior. Did they immediately rephrase their question after getting an answer? Did they copy the answer? Did they abandon the session? Did their tone change? These signals can indirectly tell you a lot about whether the interaction was successful or frustrating.
So you have to be clever about collecting it.
Exactly. And you need to be strategic about when and how you ask for or collect feedback. Maybe you prompt for feedback right at the beginning of interactions to set expectations, or perhaps you only ask when something seems to have gone wrong, or maybe when the model itself indicates it has low confidence in its answer.
Like when Google Photos asks, "Is this you?" when it's unsure.
Precisely that kind of thing. Triggering feedback requests intelligently is key.
But user feedback isn't always perfect or unbiased, is it?
Not at all. It's absolutely vital for engineers to understand the inherent biases in user feedback when interpreting it.
What kind of biases?
Well, there's leniency bias, where users tend to rate things positively just to be nice or avoid perceived conflict. There's position bias, where users often tend to favor the first option presented to them in a comparison. And there's preference bias, where, for instance, users might say they prefer a longer, more verbose response, even if a shorter one is actually more accurate or helpful.
So you can't just blindly follow the feedback.
Exactly. Understanding these common biases helps us interpret the feedback signals correctly and avoid making detrimental decisions about model improvements based on flawed data. You need to combine feedback with other evaluation methods.
Wow, what a journey. We've gone from that initial surprising explosion of generative AI applications through the nuts and bolts of foundation models, the complexities of evaluation, the art of prompting and ARG fine-tuning, all the way to optimizing inference and building these complex architectures, and finally closing the loop with user feedback. It's crystal clear that building production-ready AI isn't just about grabbing a powerful model off the shelf. It's about really careful design, robust and systematic evaluation, strategic optimization for performance and cost, and this constant cycle of iteration fueled by real-world user interaction and feedback.
Indeed. And it's important to remember, we are still arguably in the very early stages of this discipline of AI engineering. There are countless innovations yet to be built, best practices still being discovered. But understanding that probabilistic nature of these models and building systematic, adaptable workflows around that inherent uncertainty, that seems to be absolutely key to success right now.
You know, this raises a really important final question for me. As we continue relentlessly pushing the boundaries of scale, finding new sources of data, maybe even running into those bottlenecks like data and energy. And as our engineering practices become more sophisticated in managing these systems, what new forms of intelligence, what capabilities, and perhaps even what more surprising emergent behaviors might surface next from these models? And crucially, how will we as engineers and as a society learn to effectively evaluate, control, and guide them safely and beneficially in the future?
That is the question, isn't it? We're building systems with capabilities we don't always fully predict beforehand.
Something definitely for all of us to think about. Keep those questions coming, keep exploring, and we'll keep diving deep to find the answers.